Hello everyone, welcome to my class. Today I am going to cover system of linear differential equations for homogeneous case. First, some notation and definition. We use a vector function x with a two component xt, yt, where t is an independent variable. Let me review some basic definitions from linear algebra. Matrix is a rectangular array of number arranged in horizontal rows and vertical column. It is denoted by an uppercase boldface letter. For example, K is a matrix of size 2 by 2, 2 rows, 2 columns. R is a matrix of size 2 by 3, 2 rows, 3 columns. There is a special way to perform the matrix multiplications. Let me show you the example. Here is a matrix K, here is a matrix D. And let's multiply the matrix K and D. We multiply first horizontally and then vertical, and then we add them. For example, let's multiply 1 times A plus 2 times C, twice C. So A plus twice C goes here. And then the next here, 1 times B plus 2 times D plus 2D. So B plus 2D goes there. Similarly, in this spot, 3 times A plus 4 times C, 3A plus 4C. Similarly here, 3 times B plus 4 times D, 3B plus 4D goes there. Great. Identity matrix is denoted by uppercase letter I, whose columns are 1, 0, and 0, 1, size 2 by 2. Inverse matrix for a square matrix A, whose components are A, B, C, D, is denoted by A inverse. N is defined by A inverse equals to 1 over determinant of A times the matrix. This matrix is obtained from the coefficient matrix A. This diagonally we switch the positions, and this diagonally we switch the sign from A. So AD, DA, plus C plus B minus C minus B. If we have minus C minus B in this diagonal on A, then we have to make plus C plus B on this diagonal on the A inverse. Great. Let's solve a system of linear equations. That's a quick review from linear algebra. The system is x minus y equals to 5, 2x plus y equals to 5. Here x and y are unknowns, and 5 and 2 is on the right side. So let's write the system in a matrix form. This is the coefficient matrix: 1, negative 1, 2, negative 1. X and y is the unknowns column, and 5, 2 is a solution column. Then to find the value of x and y, we first find the inverse of this coefficient matrix, and we multiply through 5, 2. First compute its determinant. 1 times minus 1 is minus 1, minus from formula. 2 times minus 1 is minus 2, so 2 minus is plus, so the determinant is 1. So then xy equals to 1 over the determinant, and I need to switch the position this diagonally I need to switch the sign, which we did here, and multiply through 5, 2. This is the 5, 2. So 1 over 1 is 1. Let's multiply these two matrices. Negative 1 times 5 plus 1 times 2. Negative 5 plus 2. Negative 2 times 5 plus 1 times 2. Negative 10 plus 2 equals to negative 3, negative 8. So x is negative 3, y is negative 8. Great. Let's move on. Characteristic polynomial of a square matrix A is simply the determinant of A minus lambda equals to 0. Lambda is a number, I is the identity matrix. Eigenvalue and eigenvector. The number lambda is called the eigenvalue of A if there is a non-zero x, such that Ax equals to lambda x, and x is called the eigenvector corresponding to lambda. Now we are ready to start the topic system of differential equations. Matrix differential equations. A system of first order linear homogeneous differential equations with constant coefficients can be written as a single matrix equations in the form vector x prime of t equals to a times vector of x t, where x is in R2 and a is a 2 by 2 coefficient matrix. Great. Let's review one quick example. Write the system of differential equations x prime equals to x plus 2y, y prime equals to 3x plus 4y in a matrix form. So in matrix form, let's write in one column x prime, y prime, and the coefficient matrix 1, 2, 3, 4, and then xy. Great. A quick note, we only study a system of first order linear homogeneous differential equations with constant coefficients. It has a form vector x prime equals to a vector x, or x prime equals to ax, which we define in the star equations. Think of its solution as a vector functions. Obviously 0 is a trivial solutions, so we look for a non-zero solutions. Also note that if vector k1 and vector k2 are a fundamental set of solutions to the given matrix differential equations, then their linear combinations c1 vector k1 plus c2 vector k2 is the general solution of the system. Great. So the questions to ask ourselves: how to solve the system of differential equations vector x prime equals to ax. Here is the idea. Let's do step by step. The first step, write the matrix in A minus lambda I form, then get the eigenvalue lambda from solving the determinant A minus lambda equals to 0. The determinant A minus lambda equals to 0 is a, we also call a characteristic polynomial, which is a quadratic equation in lambda. And in the third step, get the corresponding eigenvector k after you found the eigenvalue lambda from step 2 by solving this vector equations A minus lambda I times vector k equals to vector 0 for its lambda obtained in 2. Then write the general solution in vector xt equals to c1 times a term involving eigenvalue and eigenvector plus c2 times a term involving eigenvalue and eigenvector. Great. So from this 2, solving determinant A minus lambda equals to 0 is a quadratic in a lambda, so there are 3 cases. Either we have real and distinct lambdas, or we have real and equal lambdas, repeated lambdas, or we have a complex lambda, lambda equals to alpha plus minus I beta form. In these sections we cover case A and case B. So let's start case A. Suppose we have real and distinct lambdas, eigenvalues, say lambda not equals to lambda 2, but both lambda 1 and lambda 2 are real. Then the general solution is of the form vector xt equals to c1 times vector k1. This vector k1 is a corresponding eigenvector to lambda 1, and k2 is a corresponding eigenvector to lambda 2. So c1 k1 vector e to the lambda 1 t plus c2 k2 vector e to the lambda 2t. So we fill this box by this term. c1 is the same c1, we fill this one k1 times e to the lambda 1t, and c2 is the same c2, and we fill this one by vector k2 e to the lambda 2t. Great. Let's see some example. Example 1, solve the differential equations given by vector x prime equals to the quotient matrix 1, 1, negative 6, 6, and vector x. Great. Let's follow the steps here. First, write the matrix in A minus lambda I form. This is the matrix, the coefficient matrix A, 1, 1, minus 6, 6, and minus lambda, and this I is a 2 by 2 identity matrix, whose columns are 1, 0, and 0, 1. First multiply this lambda through this identity matrix. So lambda times 1, lambda times 0, lambda times 0, lambda times 1. So you just replacing this 1 1 by lambda when you multiply by this lambda, and then subtract from matrix A. So that means we are basically subtracting lambdas from this diagonally on this coefficient matrix. 1 minus lambda, 1, negative 6, 6 minus lambda. Great. Then the next step, say the determinant of a minus lambda equals to 0. This gives you a quadratic equations in lambda. So it has two roots. In our case, lambda equals 3 and 4. So these are the eigenvalues. Next, find the corresponding eigenvector to these lambdas. So when lambda equals to 3, solve the vector equations a minus 3I vector k1 equals to 0 vector. K1 is the eigenvector corresponding to 3. Let's assume whose components are a, b. Then a minus 3i, this is the matrix a minus 3i, so which you obtain from a minus lambda I when you put lambda equals to 3. So 1 minus 3 minus 2, keep negative 6, 1, 6 minus 3, 3. Vector k has component a, b. Let's assume, we will find out later. Vector 0 has component 0, 0. Multiply these two matrices. So negative 2 times a minus negative 6b equals to 0. 1 times a plus 3 times b equals to 0. So a plus 3 equals 0. These two equations turn to be the same equations, which is a equals to negative 3b. And pick b equals to 1, then your a equals to negative 3. So now we found a first eigenvector corresponding to eigenvalue 3. One small comment here. Any set of AB which satisfy these equations works fine. So we pick B1, A is negative 3. Let's move on. Similarly, for lambda equals to 4, solve A minus 4i times vector k2 equals to 0 vector, where k2 is the corresponding eigenvector for lambda equals to 4. So again, I'm substituting lambda equals to 4 here. So 1 minus 4 is minus 3. Keep negative 6 as it is. Keep 1 as it is. 6 minus 4 is 2. Let me move on. Put AB for the vector k2. This is the 0 vector. Multiply these two matrices. Again, multiply first horizontally and then vertically and add them. Negative 3a minus negative 6b equals to 0. 1 times a plus 2 times b equals to 0. These two equations turns to be the same equations. A equals to negative 2b. Use b equals to 1, then a equals to negative 2. This is another eigenvector. Great. Now we are ready to write the solution, the general solution in this form. So what is the form here? Let me show the form. C1, first eigenvector, e to the lambda 1t plus C2, second eigenvector, e to the lambda 2t, lambda 1 and lambda 2 are eigenvalues. C1, first eigenvector, e to the lambda 1t, which is 3t, plus C2, second eigenvector, e to the lambda 2t, which is lambda 2 is 4. Great. This is our general solutions. Let's move on. Let's do example 2. Solve initial value problem. So differential equations with initial conditions given. So let's repeat the above procedure to find the general solution first, and then to find the value of C1 and C2, use this initial condition. So when x is 0, our x0 is negative 1, 4. Correct? As before, write the matrix A minus lambda I. So I'm subtracting this diagonally lambdas from A entries. So 3 minus lambda, negative 1 minus lambda, so 0 and 8 I kept as it is. Then set the determinant of A minus lambda equals to 0. This is quadratic. It gives us 2 lambda values, which will be our eigenvalues. So here we have lambda equals 3 and negative 1. Next, find the corresponding eigenvector to these lambdas. So at lambda 1 is 3, A minus 3i k1 vector equals to 0 vector. Let's solve these equations. So A minus 3i, this is the matrix we obtained from here. So put lambda equals to 3. So 3 minus 3 is 0, 8, 0, minus 1, minus 3, minus 4. and the vector k1, let's assume component is AB, and this is the vector 0 has component 0 0. Multiply these two matrices, which gives the equations 8a minus 4b equals to 0. From there 2a equals to b, so pick b equals to 2, a equals to 1. So we found a first eigenvector corresponding to lambda equals to 3. Next, let's repeat the procedure for lambda 2 equals to -1. Solve the vector equations a plus 1 times I vector k2 equals to 0 vector. Again, put lambda equals to 1 on this matrix. 3 minus 1. Now I have one more minus, so 4. 3 minus minus 1 is 4. 3 plus 1 is 4. 0 as it is, 8 as it is, minus 1 and minus lambda 0. Multiply these two matrices. This gives you equations a equals to 0. So that means b can be anything. So let's assume b is 1. So our another eigenvector k2 is ab equals to 0 1. Great. Now we can write the general solution of the given differential equations. So vector xt equals to c1 times the k1 1 2 times e to the 3t, 3 is eigenvalue, plus c2 times k2 eigenvector e to the negative t, where -1 is another eigenvalue. Great. Now let's use initial conditions to find the value of c1 and c2. What's the initial conditions? When t is 0, x of 0 is -1 4. Great. So initial conditions. So when t is 0, x 0, -1 4 is given to us. Put t equals to 0 on the right side. So c1 as it is, 1 2 as it is, t is 0, so e to the 0 is 1, plus c2 as it is, 0 1, matrix as it is, e to the 0 is 1. Great. Then let's rewrite this in a matrix form. -1 4 is the left matrix. On the right side, make a coefficient matrix. Call it the coefficient matrix. So this is 1 2 0 1 and c1 c2 unknowns in one column. Then to solve the for c1 and c2, find the inverse of this matrix and multiply through -1 4. Great. First find the determinant of this coefficient matrix, which is 1. So the A inverse equals to 1 over determinant, which is 1 by the way. And on this matrix, swap the positions. So I have both 1 1, so just 1 1, and this diagonally switch the sign. +2 +0, -2 -0. Great. So then c1 c2 equals to 1 over determinant, this matrix here, A inverse, 1 -2 0 1, multiplied through -1 4. Determinant is 1, so 1 over 1. Multiply these two matrices, again 1 times -1 plus 0 times 4, so -1 plus 0, -2 times 1 plus 1 times 4, 2 plus 4, which is 6. So -1 6. So it turns out to be C1 is -1, C2 is 6. Great. Then let's put a value back. C1 is -1, C2 is 6. Then our general solution reduces to here. Xt equals to -1, and copy this term 1 2 e to the 3t, so plus c2 is 6, and just copy this term 0 1 e to the power -t. Great. So this ends this case A. Now let's move on case B. So the case B is when our lambdas are repeated. Then our general solution is of the form vector xt equals to c1 times the k vector. K vector is the corresponding eigenvector to this repeated lambda, e to the lambda t, plus c2 plus another terms. So this terms is here. Let me go over the steps here. The first, second, third, up to the third, these are the same as what we did in the previous case. So we build the matrix A minus lambda I, we get the eigenvalue, solving the characteristics polynomials of a minus lambda I, and then we get the corresponding eigenvector k for that lambda obtained 2 by solving this vector equations a minus lambda I times vector k equals to 0 vector. And now we have the one extra step, so I put a star here. So the one extra step than the previous case is we need to get one more vector p using the vector k obtained in step 3. So solving a minus lambda I times vector p equals to vector k. Then our general solution is of the form xt. So the first term I just copied here, c1 times vector k times e to the lambda t plus c2, and this magic box, this term goes to this magic box, which is vector k times t e to the lambda t plus this new vector we obtained in step 4, vector p times e to the lambda t. Then this will be our general solutions in the repeated case. Great. Let's see some example. Solve the differential equations. Vector x prime equals to this the coefficient matrix 1 minus 9 1 7 vector x. Let's follow the steps. Find the matrix A minus lambda I. So we are subtracting lambdas from this diagonal entries of this matrix. So 1 minus lambda, keep negative 9 as it is, keep 1 as it is, so 7 minus lambda. Next, set the determinant of this A minus lambda I matrix equals to 0, which gives a quadratic in lambda. So it has two values, but both are equal. So we have a repeated lambdas, which is lambda equals to 4. Next, let's find the corresponding eigenvector for lambda equals to 4. Solving this vector equations, a minus 4i times vector k equals to 0 vector. So this matrix comes from here when you put lambda equals to 4. 1 minus 4 minus 3 minus 9 1 7 minus 4 3. And we need to find the vector k. So let's assume the vector k has component ab, 0 vector has component 0 0. Next, multiply these two matrices. Multiply negative 3 times a plus 1 times b, so negative 3a plus b equals 0. Next, negative 9 times a plus 3b, which is the same as negative 3a plus b equals to 0. So from there, b equals to 3a, so pick b equals to 3, then a equals to 1. Now we found the eigenvector k corresponding to this lambda equals to 4. Great. Next, let's do one more extra step than the previous case. Now we need to find out the vector p, solving this vector equations a minus lambda I times vector p equals to vector k. Let me scroll down. Great. So next, a minus lambda is 4i times p vector. P is the vector we need to find out. So we assume it has component cd. K vector will be found 1 3. Then a minus 4i, this is the matrix we obtained from this a minus lambda I by putting lambda equals to 4. 1 minus 4 minus 3. 7 minus 4, 3. 1 and minus 9. Let's keep as it is. P vector is cd, assume, and find the value of cd later. And vector k is 1 3, we found here. Multiply these two matrices as before. This gives us these two equations, which is same as this equations, the single equations. So assume c is 0, d is 1. So now we found a vector p whose components are 0 and 1. Now we are ready to write down the general solutions. Let me scroll up. Here is the general solutions form. So c1 vector k, which often is 1 3 component 1 3 for k vector, e to the 4t, 4 is our lambda, plus c2, and this is the magic term. So vector k times t is coming from formula, e to the lambda t, lambda is 4, plus 0 1, this is the p vector we just obtained here, e to the lambda t, lambda is 4. Great. So we found general solution for example 3. Let's move on. This time let's solve initial value problem. Example 4, differential equations with initial conditions. Let's start. Let's find the matrix A minus lambda I and set the determinant of A minus lambda equals to 0, which is quadratic in lambda. Gives us the two values, but in this case we have two values are repeated, so lambda equals to 2. Next, find the corresponding eigenvector k for this lambda. Solve the equations. A minus 2i times vector k equals to vector 0. So this matrix comes from this, from A minus lambda I. Put lambda equals to 2. 1 minus 2 minus 1 minus 1 1 3 minus 2 is 1. I substitute lambda equals to 2 on A minus lambda I, okay, not on the determinant. Okay, we skip that matrix A minus lambda I form here. So times, this is the vector k, we assume has component a and b, so we'll find out later. 0 vector has component 0 0. Multiply these two matrices, and that gives you the vector k, which is eigenvector corresponding to this lambda equals to 2, is component minus 1 and 1. Next, find another vector p vector by using this k vector on this equations, which is A minus 2i times vector p equals to vector k. So again, A minus 2i is this coefficient matrix, which is the same as this one, and assume p vector has component c and d, and we will find out later. And vector k, we just obtain here negative 1 1, put there. Multiply these two matrices as before, and then equate to negative 1 1, which gives the equation c plus d equals to 1, and assume d is 1, then c is 0. So we found vector p. Now we are ready to write the general solutions. So general solutions, vector xt equals to c1 times, this is the k vector, which is here, e to the lambda t, lambda is 2, plus c2, again k vector, times t times e to the 2t, plus p vector 0 1 times e to the 2t. So this is the general solutions of this given equations. So let's find the value of c1 and c2 using initial conditions when t is 0 or x0 is 2 6. So 2 6 when t is 0, x of 0 equals to c1, this is the negative 1 1 matrix, put t equals 0, e to the 0 is 1, plus c2 when t is 0, this term 0, so just 0 vector, plus 0 1, e to the 0 is again 1. Then write these equations in matrix form. So 2 6 is a matrix on the left side. Collect the coefficients and make a coefficient matrix, minus 1 1 0 1 0 1, and c1 and c2 are unknowns in one matrix. So our goal is to find the value of c1 and c2 from this matrix equations. So the idea is first find the determinant of this matrix, and then find the inverse and multiply through 2 6. By the way, its determinant is negative 1. You multiply negative 1 times 1 minus 1 times 0 0, so negative 1. So then c1 c2 equals to 1 over determinant of this coefficient matrix, which is negative 1, and this matrix we need to switch the positions, and this diagonal we need to switch the sign, we need to put the minus. Great. Multiply to 2 6, multiply these two matrices and multiply this minus. So 1 times 2 is 2, plus 0 times 6 0, so 2 plus 0, which is 2, multiply by this minus later, gives you minus 2, and minus 1 times 2 minus 2, plus then minus 1 times 6 is minus 6, so minus 2 minus 6, which is minus 8, multiply by this minus, so it gives you plus 8. So we found c1 is negative 2, c2 is 8. Great. Now we can reduce our general solution to a particular solutions by substituting values of c1 and c2 on the general solution. So here c1 is negative 2, and copy this term, negative 1, 1 e to the 2t, plus c2, which is 8, and copy these terms from the general solutions, which is negative 1, 1 times t times e to the 2t plus 0, 1 e to the 2t. Great. So we finished these sections. Thank you.